All right, so we've got the sample problem. It is an inclined plane problem, a block on a ramp. So there we go, we've got our block, it has a mass. They tell us the length of the ramp. It's L. They tell us the angle that the ramp is up above the horizontal. They even tell us the height of the ramp. What else do we know? Well, I guess we have actual numbers for all of those. Mass is 0.4 kilograms. The length of the ramp is 2 meters. The height of the ramp is 1 meter. The angle is 30 degrees. And it wants to know how fast is it going at the end, which is right here when it gets to the bottom. I guess they also say that it starts from rest. So the initial velocity at 0 up here. So clearly we know how to do this using the Newtonian model. But can we figure out how to use the energy and work model to do this? Well, work is equal to the change in energy. So work, I guess we need to know what forces were acting on this, and energy, well, we know something about the initial kinetic energy. We have the velocity and we have the mass, so we can find kinetic energy at the start, and we're interested in the velocity at the end, the speed at the end. So with mass and that, we got something about the final kinetic energy. So this looks like this is okay, maybe this is okay. I guess the first thing we're going to need to do is draw out the forces so we can get the net work. So it's back to a force diagram, just like it would be if we were doing the Newtonian model. So what are the forces acting on this? We're told it's a frictionless ramp, so there's no friction. There's a surface here, so no friction, but there is a normal force pointed up perpendicular to the surface. There's gravity for sure, because we're by the surface of the Earth. What else? No ropes, no springs, so this is pretty much it. So of these forces, which ones do work? Well, how's the thing actually going to move? It's going to move down the ramp. So I'm going to go ahead and draw in my displacement. Displacement will be like that. It's a different color, so we know it's not a force. So the normal force isn't going to do any work. So here, when we're figuring out the net force, the net force is going to be the work, the net work. The net work is going to be the work done by the normal force plus the work done by gravity. And we are told that the work done by the normal force is 0 because the normal force and the displacement are perpendicular to each other. Now gravity isn't completely parallel or anti-parallel to the displacement. It has this angle here. And I guess if we look here, we can say, well, this angle here, that's going to be 90 minus theta here, because here that's the same as this down here. That's the direction gravity would point. We know this is a right triangle here, so knowing that the interior angles of a triangle have to add up to 180 degrees tells it that this has got to be 90 minus our angle. So we can get the work done by gravity. The work done by gravity is equal to the magnitude of the force of gravity times the displacement. I guess it travels the whole length L down the ramp, so that's going to be its displacement. Let me replace that with an L, just so I'm consistent here, times the cosine of the angle between them. And force is pointing this way, and L is pointing that way, so the angle between them is 90 minus theta. And I'm going to stop you right there and say the cosine of 90 minus theta. Let's go back to this triangle. The cosine of 90 minus theta, well, this is the right angle. If this is 90 minus theta, that's this side times L times the cosine of 90 minus theta. But this is also equal to L times the sine. It's the opposite of theta. So maybe that's a little confusing. You can get out your calculator and convince yourself. But I'm claiming, looking at this triangle, cosine of 90 minus theta is the same thing as sine of theta. because here's the adjacent side to the 90 minus theta angle, but this side is also the opposite side to the angle theta. So if we multiply L by sine of theta, I guess we'll take force gravity along for the ride. We're still calculating the work. That's the height. We can go ahead and plug that in. And then we can plug in what we know about the force of gravity. It's mass times g, as usual. So that's the work done by gravity. It is the mass times g times that height difference. It started up here and then it moved down. That's the work done by gravity on it. All right, so we've got now the work done by gravity. We know that there's no work done by the normal force because the normal force is perpendicular to the displacement, so we have the net work now. The net work is just the work done by gravity, and the work done by gravity is mass times g times the height that this thing has moved, the change in height. All right, next we need to figure out what's going on with the change in energy, because the change in energy is going to be equal to this net work done on it. Okay. Change in energy side of this equation. Well, we have a final kinetic energy minus an initial kinetic energy. No other energies are changing here. We'll talk more about that later, but for now you can just take my word for it. Kinetic energy itself is equal to 1/2 the mass times the speed squared. So the final kinetic energy would be 1/2 mass times the final speed squared. And the initial kinetic energy would be 1/2 mass times the initial speed squared. And what do we know? Well, I've written it differently here. I have it as v0, but that is definitely the initial speed. So the initial speed is equal to 0, which means that the initial speed squared is equal to 0, which means that anything times that, all of that is 0. Okay, so the change in energy is just equal to 1/2 the mass times the final velocity squared. So now we can put this all together. The net work is equal to the change in energy. That is the work energy theorem. The net work is equal to mass times gravity times the change in height. This block went down. The change in energy, because the initial energy is 0, is just equal to that final energy. And now we can go ahead and solve for v. But I'm going to erase this and give myself a little more room so I can do that. All right, so we're using the work energy theorem, and we found the net work. It's equal to mgh. And we found the change in energy. It's equal to 1/2 m times the final velocity squared minus 0, because the initial energy was 0. Now we want to solve for the final velocity. So we should multiply by 2 on both sides of the equation, get rid of that 1/2, divide by m, get rid of that m. Oh, and it goes away over here too. So we got 2 times g times h equals the final speed squared. Take the square root of both sides of the equation so we can get rid of that squared. And there we've got a nice expression for the final velocity. Let's go ahead and plug in the numbers. Turns out we didn't even need to know the mass. And the height, that's 1 meter. I'll put my final speed over here. 2 times 19, or 2 times 9.8, that's 19.6 units. Meters over second squared times meters, that'll be meters squared over second squared. And we will get about, let's see, look at my calculator. We will get a final speed, I'm going to write it up here because I'm just out of room, of 4.4. That's the square root of 19.6. And the square root of meter squared is meters. And the square root of 1 over second squared is 1 over seconds. And that's the units we want for final velocity. So that's how we could use this work energy theorem to find final speeds. And you'll notice we didn't have to do components, except we kind of did when we figured out the work. We had to be a little careful that we were only using the bit of gravity that was parallel to the displacement. Well, great. Now that we've figured out the speed, now they've asked us about how much power is generated by gravity. All right, so I replaced our final speed. Now we figured that out, and now we want to know about the power generated by gravity. And power is equal to the change in work over the change in time. But here our work is done constantly. It's done by a constant force, so we can just actually do a straight up change in work over change in time, not the derivative. And we know the work done by gravity is mass times g times the height. That is the final amount of work that's done. The initial amount of work is done is none because it doesn't do anything before you start the problem. Similarly, t is, well, it takes us a time t to do the work, and at the start of the problem we start the clock and there is no time having passed. So that's a really boring difference that we have to do, but just to remind you what's happening. All right, so we know mass, we know g, we know h, and we know t. We are told t is 0.8 seconds. So the power generated by gravity is going to be the mass, which is 0.4 kilograms, gravity 9.8 meters per second squared, height 1 meter over 0.8 seconds. And if you plug that into your calculator, you will get 4.9 and then the units. All right, so we'll get kilograms, meters over second squared. That's these first two. I'll bunch those, times meters over seconds. Kilograms, meters over second squared, that's newtons, mass times an acceleration. So those are newtons. Newtons times meters, that's watts. And here I'm actually going to start writing out what these units are. I'll erase my free body diagram. So units of work and energy, those are watts. W, also like work, that's a little unfortunate, but watts are equal to newtons times meters. So newtons times meters, that's what we got here. This is watts. Units of power are joules. We use a J, and joules are equal to watts over seconds. So we ended up getting the power of 4.9 joules, and of course you wouldn't in general use blocks sliding down inclines to generate power. You know, joules, the unit that you may be more familiar with here for power is going to be horsepower. So you can just do unit conversion between those two, but so we don't generally have blocks falling down inclines to get power, but we do sometimes have water falling down waterfalls to get power. So a little bit of an artificial situation, but related to another situation that you might find. So that's how you can do a work energy problem.